Hello friends, after a long break we are meeting again. The present video deals with the direct displacement based design of dual system, that is frame shear wall system. This part 2 where we shall be taking up the numerical application with respect to the topic. We have studied in the last video that there are several tables that are to be prepared for getting the final solutions. One of the tables is the calculation of height of inflection of the wall. So in this video we shall be taking up that computation of the height of inflection of the wall. So frame shear wall building we have seen earlier also. The frames are the beams and columns and shear walls are there on the peripheral lines of the building and on the opposite sides of the periphery. As shown in the plan, the 4 shear walls are here. There can be more shear walls. However, in each direction shear walls are to be provided and they are to be shadow image of the other so that there is no twisting moment. A cross section of the wall is shown here and the length of the wall LW is indicated through the arrow in this figure. A shear wall is a cantilever system fixed at the base and having the width equal to LW. So it is nothing but a deep beam having large depth. Depth is equal to LW. The frame bends in some curvature and shear wall bends in bending curvature, and so they interact with each other because they are monolithically cast. And the final pattern will be something like this. The wall bending moment is shown by the colored line, and the frame bending moment or overturning moment is shown by this line. These are relative values that we shall be understanding when we take up the numerical. And because of the change of curvature of the system, there will be an inflection point of the wall where the curvature is changing and the bending moment is 0. So this height is to be calculated for further calculations in the system. The frame is to be designed for a particular amount of base shear which varies from 20% to 35% of the total base shear in the system. The yield curvature of the wall is given by twice epsilon y by LW. Epsilon y is the yield strain of the rebar. So rebar is 500 megapascal divided by modulus elasticity of steel. There will give the strain. Then this formula gives you the yield curvature of the wall 0.001 per meter. This will be required not in the current video but in the future videos. The point of control fracture of the wall is to be also computed as we have studied in the last video. Now in the last video we have seen there are several tables which are to be prepared for numerical solution. One is this table for inflection height of the computation, inflection height computation, then table for equivalent single degree of freedom system properties computation, table for frame ductility computation, table for base shear distribution. So one by one we have to take up this. Each of these will take time in the explanation, so we will not take all the tables together. Today we shall be taking only first one, table for computation of the inflection height of this wall. The numerical example is here. Find the lateral design forces in floors for a 10-story dual system, that is frame shear wall building, which is to be designed for 2.5% drift. As you know, the direct displacement based design can accommodate only one design target objective, that is drift. So we have taken that one, 2.5% drift. The yield strength of the rebar reinforcement is 500 megapascal. Diameter of the longitudinal bar is 20 millimeter. Inter-story height is 3.4 meter. Ground story height is generally more because of the foundation, so it is 4.4 meter. Floor mass is 10,000 kg in each floor and the roof mass is slightly less, 6,000 kg. Assume that the frame takes 35% of the base shear. Length of wall is given 5 meter. Length of beam is given 5 meter. Depth of beam is given 0.6 meter. Take post yield stiffness ratio 0.1. That is the after yielding and before yielding ratio of the stiffness. And the hazard level for which we have to design is given here. Hazard level is EC8 Eurocode 8 spectrum for soil type B at 0.4 G seismicity level. So in this question, the data those are given are written like this, and the number of stories 10, theta D, design drift is 2.5% means 0.025 radian, Fy 500 megapascal, dB, diameter of the longitudinal bar 20 mm, HS interstory height 3.4 meter, HG ground story height 4.4 meter, LW length of wall 5 meter, LB is not shown here, LB length of beam is also 5 meter, and R the post tilt stiffness ratio 0.1. Frame shear apportionment is 35%, that is 35% of the total base shear will be taken by the frame and rest 65% will be taken by the wall. HB, what I said, HB is here at 5 meter, hazard level ECH at 0.4 G level. Now for computation, we will take up the help of Excel sheet. So in the Excel sheet, I have written down columns which are required. So the floor numbers and column numbers are given the numbering here within parentheses. So second column is for masses, then heights of the floors, then product of MIHI, and MIHI by sum of the MIHI, which is proportionate values. BTI total shear, BF the frame shear, BW the wall shear. The relative what is given here, because these are not the absolute value for design purpose, these are relative values considering unit load etc. and some distribution, which is alright for the purpose of computation of inflection height of the wall. MOTI is the water-turning moment in the wall for the ith floor, and MW is the moment in the wall we shall compute. So MOTI, the seventh column, MOTI is given by this formula, MOTI of the higher floor, that floor above, plus shear in the floor above into distance between the floor above and the current floor, that is interstory height. So the moment we are talking about is nothing but for a lateral force applied on the building, what is the moment at different levels? I is the floor level. Similarly, the wall moment MWI for the higher floor is given by MWI plus 1, that is the in the upper floor whatever moment in the wall, plus upper floor shear in the wall into interstory height HI plus 1 minus HI. So this simple formula that will apply through Excel sheet, and we shall calculate the values of MOTI, MWI. So far there is no problem. BW, the relative shear in the wall, it will be equal to this total shear in the column 6 minus shear in the frame BF in column 8. The total shear will be obtained with the relative placement of loads. The loads that will place in the different levels are this MIHI divided by summation MIHI. So these are all relative loads, value will be less than 1, and these loads will be placed laterally on different floors, and this will produce some shear. So those shears we shall put up here. So as you know, shear goes on cumulatively adding up. So column 6 BTI is the cumulative sum of the column 5. So let us start. Now floor 1 at the top or floor 10 at the top, it is 10-story building. So we shall put the highest story at the top and gradually we shall go downward. So we shall put here 10 story, and gradually we shall reduce the value. So we can take the help of the Excel here, equal to this minus 1, and we can drag the formula to get the other floors. So this minus 1 we don't require. 0 means the foundation ground level, last one. This is first floor and this is ground level. Ground level value also we shall require for moments etc. Now MI, the mass in the top floor is 6000 kg as given in the question. So write down here 6000, and let us increase the size of the fonts. So this 6000, next floor level loads are only 10,000. So this is constant 10,000 to all levels. So after first floor it is all 10,000, and at the roof it is 6,000. So this is 10th story or roof level, and this is first story and ground level. Okay, heights, we can start from the bottom, because bottom height we know. First floor height is the ground story height, which is 4.4 meter given. Okay, and all the interstory heights are common, 3.4 meters. So if we add up with this, equal to, I will take the help of Excel formula, this plus 3.4, the height of the other stories. So this gives this value, and this formula you can drag upward. Yes, so these are the heights of the floors. The roof level height is 35 meter from the ground. This height you can write down here, it is 0. Ground level height is 0. Now the product of these two we have to take, so equal to mass product this height equal to, so, and this we can drag downward and get all the values, and you can increase the size. So this is the MIHI product, and here you have to take MIHI divided by sum. So let us take the sum here, sum of this column here to here. So this is the sum MIHI product. So this fifth column are the MIHI value given in fourth column divided by this sum. So I can write down here equal to this MIHI divided by this product. Now since this product is a constant value, we have to put a dollar sign here. Yes, so you see it will be always less than 1, because sum is always more than the individual values. So we drag this and get the formula. So these are the ratios here which will form the lateral forces. So we are putting lateral forces on the floors in the proportion of this MIHI divided by sum, this one. So these are slightly arbitrary, but not exactly arbitrary. They are taking the given values of masses, then taking the values of heights, etc. And these are the relative values that we are putting as lateral forces to calculate the shear and other parameters. That's why we are always writing the word relative here, not the absolute value. So the first value will be equal to this shear value at the top. Second value onwards will be sum of the previous value plus sum of the force that is applied at the current story. So this is this, and this formula we shall drag up to the bottom. So these are the total lateral shear at different floors. Total lateral shear at different floors. You see, because it is this MIHI divided by sum MIHI, so last value become 1. This check of accuracy. Moment MOTI, column 7, is to be found out from this formula. Previous moment, that is upper story moment plus upper story shear into interstory height for the current story. Very simple. There are several lateral loads, so if you find the moment will be certainly found out from these values only. Now at the top, the distance is 0, so this value of moment MOTI is 0. Frame overturning moment is 0. So let us apply this formula to calculate other moments. So equal to the previous moment MOTI plus 1, this one, plus the previous shear, that is shear in the other upper floor, this star, difference between the heights, that will give the interstory height. So equal to, you can put the heights, this height minus the next height. Now you could have also given the directly the interstory height ratio. Now in some buildings it can be so that the interstory heights are changing. That's why this formula will be generalized. Better to use this formula. And we can drag this to get the other values. These are the overturning moments. Now overturning moments will be also at the ground floor means ground level, up to ground level, because above the ground level you have the lateral loads, so they will be producing moment also at the bottom. So we can drag it to the ground level where the storage is 0, height is 0, and the value is this. So these are the overturning moment in the frame. Now BF is the relative value of the shear in the frame. Now for this purpose, shear in the frame, let us go back to the, yes, here you see the frame carries 0.35% of the total base shear. Because it are relative, so we can put 0.35 as the relative value. So this force is put at the top of the frame. So BF will be 0.35. Now we shall not put any other loads here for the frame, and this will be a triangular diagram, and everywhere the shear will be constant, 0.35. Okay, so frame shear will be 0.35 in all the rows of the Excel sheet. Let us go back to the Excel sheet again. So frame is 0.35, and this is constant over all the floors, so we take it like this, 0.35. These are relative values, so that's why. Now the frame apportionment could be something different, maybe 25%, 30% or something other, and accordingly we will put that fraction here. Now wall relative moment is nothing but the total relative shear, the wall relative shear BW in column 9 is equal to total shear minus the frame shear. So you just do it like this. This is equal to this total value minus the frame shear value. So this can come negative also. It has come negative here. Now let us drag this and we will get the values. So these are different BW wall relative shear values. Now the wall moment can be obtained from this formula. Current level moment equal to higher level moment, immediately higher level moment plus immediately higher level shear into interstory height for the current story. So as earlier, equal to, this will be 0 because at the top distance is 0, so this is 0. This equal to this previous moment plus previous shear in the wall, this one, multiplied by the height difference here. So height is at the above story is 35 minus this one. So this is the value. So these are the wall moments, relative values of the wall moments, and it has to come up to the bottom because at the bottom there also will be a moment. So let us put it like this. So this is the ground level moment in the wall. So this table will not help you in the design because the actual values are not put. These are all relative values with certain principle. The principle is in the wall you are putting the total shear we are putting in proportion to the mass height product divided by sum of the mass height. These are the total shear we are assuming, and frame shear is based on the proportion of the base shear it is taking, so it is 35%, so 0.35. If you subtract this total from the frame shear from the total, you get the wall shear. So these are relative values. This will not help in the design. These are only for calculating the height of inflection of the wall. Now what is the height of inflection of the wall? Height of inflection of the wall is where the bending moment of the wall is changing sign and it is 0. So you see here it is negative and here it is positive. So obviously the height of inflection will be lying between this 21.4 meter and 24.8 meter. By interpolation you can get it, but the interpolation will not be very correct because the wall moment we have seen in the beginning, it is a curvilinear line. Diagram is curvilinear, so direct straight line interpolation will not give you correct value. So let us draw the graph for this. Let us insert a graph. So we are putting line graph, and the horizontal value will be the moments. So x-axis is there, are the moments of the wall. So these we shall put along the x-axis, and y-axis are the heights of the building. So in the y-axis, let us put this column, which are the height column up to 0, and this is the wall bending moment diagram. So somewhere here it is 0, so we have to establish where it is 0. So you can put here the axis titles, and what is the axis title here? This axis title is height in meter. And this axis is the wall moment. Basically it will be kilonewton meter, but these are relative, that you can write here, relative values. So wall moments are there. These are the wall heights. This number has become decimal, so many places of decimal. Let us reduce this decimal place to say 1, and you can bolden it. This, if you want to transfer to your Word file, or you want to submit some assignment for that purpose, so we can go to font and bold and black color or whatever color you want. Similarly for the y-axis, alright, so this is the graph, and we have to locate this point where it is 0. So location can be done by a trick, by writing a horizontal line here. So we put the value of x and put the value of y. Now you see here it is -2 is given, so we can put here -1. -1. So -1 to on the right hand side you can give 1, so that you get a distance of 2 meter, and y value will lie between, as we have seen, it lies between 21.4 and 24.8. So you can start something 21.6, 21.5, and it should be same at the same level. So this is also 21.5, and add this to your graph. This color let us change to something bright, and it is good to use smaller thickness here for the time being, so that the accuracy is obtained in the calculation of inflection height. Now this we want to add up as a new graph, so select data and add, then x-axis are these values, and y-axis are these values. So you get a horizontal line, and these two lines should meet exactly at the point where it is 0. Now whether it is exactly met or not, we can see by enlarging the scale of the graph, and you can see here it appears it is slightly lower. Or how much we have given? We have given 21.5. Let us increase it to 21.6. and see what has happened. Yes, now you see it is exactly almost matching. If you decrease this thickness, then you can exactly understand. Yes. So inflection height is now 21.6 meter. You can write here. You can write here. Inflection height, if you remember, we have written HINF equal to 21.6 meter. So this is the inflection height of the wall, which we shall be utilizing later on for other purposes. So I think it is clear how it has been done. If any confusion, you watch the video again, and I think it will be clear. Thank you. Please subscribe the channel, share the videos, like the videos, put your comments, put your queries. I shall be glad to answer those things. Thank you very much. And I also wish you happy Dasara, the Dashami Puja of Ma Durga today. I wish you all the best.